Okay, welcome to Level 1 Science Online with Henny van Vieren.
Hey, Year 11s, welcome back. Term 2, here we go. I hope you all had a good break. Um, I know we couldn't get away, but at least I hope you had some good times at home. Alrighty, last term um, we started looking at motion and acceleration and speed and distance time graphs and acceleration time graphs and all of that. We now need to move on to forces. And we've talked about forces a bit in class already. But without further ado, let's specifically start looking at forces. If you are following along, it is PowerPoint number 3, any forces mass. Okay, so here we go. So for this, our learning intention, we need to know mass, weight, and the acceleration due to gravity, balanced and unbalanced forces in context of everyday experiences such as being stationary, moving at a constant speed, and accelerating. And then there's your near connections, and there's no wider connections in here. Okay, so what is a force? A force can cause an object to change its velocity or movement. It's a push, a pull, a tug, a heave, a squeeze, a stretch, a twist, or a press. Okay, it can change the shape or it can change the movement. When we talk about movement, it's going to change the velocity. And when we change the velocity, we call that acceleration. Alrighty. So remember, a something will only accelerate when there's an unbalanced force on it. Now there's different types of forces. We have contact forces and non-contact forces. A contact force is obviously when there's contact between two things. Um, so if you are physically pushing a cart or your bicycle or anything, that is a contact force. Or your shoes that are gripping the floor, that is friction, that is a contact force. But a non-contact force are things like magnetism, where you can't see it, but you know it's there. And gravity. Can you see gravity? No, but you can see the effects of gravity because they're not all floating up in space. So these are some non-contact forces. Okay, so think about contact forces, buoyancy and surface tension. That is because something is floating. Thrust force. Thrust force is an action and a reaction force. So remember, for every action, there is an equal but opposite reaction. So the amount of thrust being pushed out the back of an aeroplane or a rocket will propel that thing forward depending on the amount of friction that it has. And the friction in this case is going to be air friction. Okay, so these are all contact forces. Non-contact, we talked about gravity, electrostatic forces, and magnetic forces. Okay, so thrust requires some part of an object, whether it's a gas, liquid, or a solid, being pushed forcefully from itself. Rocket fuel from a rocket, for example, once the rocket has left the thrust, it's no longer present. It requires a reaction, actual thrusting. If you want to go and read something interesting, you can read about the ion drive, which is a type of engine that NASA is working on, the ion drive, where they literally want to use ions to eject them from the back of a vehicle. It's going to be a very weak engine, but it's going to take almost no fuel. But every time you release an ion, you push it away. And when you push it away, it pushes you forward because there's an action and a reaction force. And that would be eventually very slow acceleration because the force is going to be very small, but eventually it'll be so big that it can um, it can propel a spacecraft forward in when there's zero friction in a frictionless environment. Okay, so acceleration is the state of an object due to the force applied. It has to be an unbalanced force. Remember, Newton's law says that an object at rest or in motion will remain at rest or at motion unless an unbalanced force is acting upon it. So if you're going at a constant speed and your speed is not changing, then all the forces are balanced. So if you're going down a slight hill with your bicycle, it's not making you go faster, but you're also not losing any speed. Then the friction on your wheels and the other friction in your bicycle being is exactly being balanced by the gravity pulling you down the hill. Okay, so that is means that when there's no acceleration, all the forces are balanced. If something is just lying on the table and it's just lying there, the table, the gravity is pulling it downwards, but the table is pushing it back up. We call that reaction force. And because those two forces are balanced, that thing will not move. Okay, so please remember that. We always look, excuse me, we always look at forces as pairs. So you can see on this aeroplane we have the thrust force out the back, and that gives us acceleration towards the front. Now, when you have something going through the air will try and slow it down, and we call that friction. So here your thrust is overcoming the friction, so it's an unbalanced force. Friction is a force that opposes motion. So two surfaces might feel smooth. Now, when you look closely, there's always, even at a microscopic level, there's always going to be rough surfaces. And those rough surfaces try and hook into each other and prevent things from moving around. So if you're walking on, for instance, a road, the road surface is usually rough. Hopefully, you haven't fallen off your bicycle on the road much, but you know that if you fall off there, that roughness, that friction that you're experiencing on that road surface is the one that takes off your skin. But if you've ever been ice skating, you know that there's very little friction on the ice skating rink because the water is actually filling these gaps between you and the ice. Because as you going over it, there's water between you and the ice, and that helps you to have a very low friction rate. Or if you're running around in, I don't know, a highly polished floor on in your socks, there's very little friction. Okay, so you can easily fall. But if you put on your sneakers with good grippy rubbery soles, those rubbery soles will actually shape and go into the little holes that are available and have a high friction. Okay, so friction opposes motion. It's very, very important. Okay, so gravity is a force that acts between bodies even though they are not in contact. Okay, so why is the moon not flying away from the Earth? Because the Earth's gravity is pulling the moon towards it. But at the same time, the moon is going around it and trying to get away, so those forces are almost in balance. The moon is actually going away by about 2 centimeters every year. So in 100 years, the moon is going to be 2 meters further, so it's not a big deal. But it is actually moving away from us. The, the reason why we know that is when the astronauts went up and landed on the moon, they took along some mirrors and we placed them on the moon so that we can shoot a laser at them. And they did that once a month for years and years and years and years. And so you shoot the laser and it hits the mirrors and some of the light comes back. And then they calculate how long does it take to get there and how long does it take to get back. And that's how they calculated that the moon is actually going away from the Earth ever so slightly. Anyways, but when you have any object, there's going to be gravity between them. So, if you are actually being pulled with gravity towards the sun, but you can't feel it because the gravity of the Earth is so much bigger. Okay, but the further away you are, the weaker it will be. Did you know that even if you're sitting next to each other, let's say you're going to the movies and you're sitting almost about a millimeter apart, you and somebody special, that is the same amount of gravity between the two of you because your bodies are attracted to each other with gravity because anything with mass, anything with that is massive, anything with molecules will attract something else. Now that force of gravity between you is the same force that you experience from the sun, just for interest sake. Okay, but if we're on a bigger planet with more mass, you will have more gravity. So with everybody trying to go to Mars these days, Mars has got a lower gravity than Earth because Mars is smaller than Earth. When they went to the moon has got a 1/6 of the gravity that the Earth does. So 1/6 mean that if you were, um, what is it? Let me just think. If you're 120 kilograms on Earth and you divide that by 6 on the moon, it will feel as if you are 20 kilograms. So you're going to be really strong. Okay. Feel that you're really strong and pick up huge boulders and stuff. And here is just the acceleration caused by gravity. So the Earth is pulling you downwards every day, every moment of always. The Earth is pulling you downwards. Okay, and it's pulling you downwards with a force, and that force is called weight force. Now, you are currently sitting, and your bottom is on a chair, and the chair is pushing back up. Otherwise, you would be falling to the floor. And eventually, if you fell on the floor, that floor will be pushing up. Okay, so these are, it's called support force. When we are in water, gravity is pushing us down, but buoyancy is pushing us up due to the density of the water. And density now plays a role. Okay, but in general, if you're on a solid surface, it's going to be gravity and support force. Now, Isaac Newton was the guy that everybody says that, and we don't even know if it's the truth, but if the apple actually fell on his head. But he did see an apple fall. He wasn't the first person to see an apple fall, but he was the first person to actually see an apple fall and say, why? Why does it fall? And how can I investigate that further? So, yeah. Now, Newton's first law says that if forces acting on an object are balanced, then the object will remain stationary or carry on at the same speed in the same direction. We've said this many times. To put it in very simple words, something that is doing nothing will keep on doing nothing until you push it. Okay, an unbalanced force. Or something that does something at a constant speed will keep on doing that unless there is an unbalanced force on it. So, if this car is driving at exactly 100 kilometers per hour at a constant speed, the thrust from the engine will be equal to the friction of the wheels, of the friction of the air, friction in the bearings, everything. Because this thrust force is not overcoming the friction force. So can you see that when we draw these arrows, you have to think about the motion of the object. This car is traveling forwards, so we have the thrust pushing it forward, and we have the friction opposing that. It's not pulling it back, it's opposing that. Okay, we have gravity pulling it down, and we have the ground, or the motorway, pushing it back up. So balanced forces is constant speed, or it is stationary. Okay. Again, we just talked about this already, but we always talk about them in pairs. So the up down and the left right, or forward and back. So when forces are balanced, an object will either remain at rest or travel at a constant velocity. So just for interest sake, humans, when we skydive, the maximum speed that we can reach, maximum velocity we can reach, is about 220 kilometers an hour, because at that point the air friction in our atmosphere is pushing, or is pulling us, no, not pulling us back, but is countering the gravity, and you cannot fall any faster. Think about that video that I showed you regarding Felix Baumgartner. Go and watch it again. It is a really cool video. But he was falling at the speed faster than the speed of sound when he was out of the atmosphere. But as he came into the atmosphere, he slowed down significantly. So yeah, and that is why. It was all because of friction. Alright, so Newton's second law. If an unbalanced force acts on an object, then the object will accelerate in the direction that the net force acts. So in other words, if you are in your car and you slam on the brakes, that force is friction that you're creating, and it is against the motion, which means it's going to slow you down. Look at this. We are going forward, and our acceleration, because you can see this thrust is way bigger than the friction. It means we are accelerating, but we're accelerating with the direction of motion. Very important. We are accelerating with the direction of motion. If he was slowing down, this friction would have been higher because he's slamming on the brakes. And then the acceleration will be against the direction of motion. Okay? But balanced forces, when your support force and your weight force is the same as your drag and your friction. We've just said this again. Okay? So in this case, you can see this force. So they can actually ask you to calculate the forces. So if you have this force of 120 newtons in this direction, and you have this force of 13 newtons in that direction, you take the bigger force and you subtract the smaller force. So 120 minus 30 is 90. Okay, but you have to give a direction, accelerating the object from right to left. Okay, in this case, the car is going, the Lamborghini is going forward. Okay, so with the motion. If there are two forces acting together, you add them. So force 1 in this case, you have that, let me just get the pointer here so that it's easier. You have this one opposing both these forces. So consequently, if you add both of these up, it would give you 120, but the opposing force you have to deduct from that to give you 90. Okay, so this was a question in one of the past papers. So referring to the force diagrams in part B, explain the link between the net force acting on the runner in sections A, B, and C of the graph. And remember, in those graphs, you can see when it's acceleration, when it's constant speed, and when it is deceleration, and when it is stationary. So, in all of those, you need to be able to say what is happening with the force. So, in section A, first of all, define net force. Net force is when it is the net force acting on something when considering all the. So a net force is the resultant force when multiple forces interact. If the forces are pointing in the same direction, the forces add up, giving a larger net force. If the forces are in opposite direction, the forces subtract, giving a smaller. Okay, so in this case, the thrust is bigger than the friction. What's happening in section A? You see gravity and support is the same. So he is accelerating in the direction of motion. Over here, thrust is the same as friction. Support is the same as gravity. Everything is balanced. What is happening here? He's still moving. He is at constant speed. And now, his thrust is smaller than his friction. He's slowing down. And gravity and support are still the same. So that is a negative acceleration. I hope that makes sense. Now, negative acceleration is a net force against the direction of motion. Okay, so it was in 2013 that they asked this. Beside each diagram, state if thrust is greater than friction, thrust is equal to friction, or if thrust is less than friction. The gravity and support forces have been done for you. Okay, and you have to draw these arrows. Now when you draw these arrows, guys, you need to make sure that the one is bigger than the other if they are accelerating or decelerating. And if they are at constant speed, you need to make sure that they are the same size. Okay. So section A was acceleration. We've just looked at that. section B constant speed, and then deceleration. Referring to your force diagrams in part B, these explain the link between the net force acting on the runner and the type of motion. So you need to then say in your answer, describe what is meant by net force, explain the link between net force and motion for each section. That's when we say the net force is greater against motion or with motion, or there's no net force. Compare the direction of the net force. And this is for excellence, so it's really not that difficult. So net force is the resultant force when multiple forces interact. If the forces are pointing in the same direction, you add them, giving a larger net force. If the forces are in opposite direction, you subtract them, giving a smaller net force. Net forces determine whether the runner is accelerating, decelerating, or constant speed. If the net force is pointing in the same direction as the direction of motion, then it accelerates. Did you get that? If the net force is pointing in the same direction as the direction of motion, the object accelerates. If the net force is pointing in the opposite direction to the direction of motion, the object decelerates, which means there's no net force. The object maintains constant speed and is stationary. Okay, so with our runner here, our net force is going to be the resultant force. That one is equal to that one, so they cancel out. This one is bigger than this one, so the net force is going to be in that direction. Okay, so it's accelerating him with the direction of motion. This is no net force, so it's constant because they're all equal. And over here we have our net force in that direction. He doesn't suddenly start moving in that direction. That's not the case. The net force is simply against the direction of motion, which means he is slowing down. Please do not get confused with those two. So in 2015, we talked about the kereru about the kereru, which is the wood pigeon. Now, if you look at these two, one of them, oh well, you can see, the only horizontal forces are shown in these diagrams. Assume any other forces are balanced. So gravity and support force or lift in both of these cases do not count. So you only need to worry about the horizontal forces. Now in this case, the kereru is flying somewhere, but it is going there at a constant speed because there is no acceleration, because there's no net force. These are equal, so they are subtracted from each other. In this case, which way is the kereru being accelerated? It is being accelerated into the right side of the paper, because our right, or in, I don't know if that is forward, but towards the right, the net force is greater towards the right than towards the left, which means he is being accelerated in that direction, but it is, well, slowing him down in this case. So there was a diagram. The bird had a constant speed, so oh no, so this is the diagram. The bird has a constant speed, so the net horizontal force is 0. In B, the bird is slowing down, so it is decelerating. An unbalanced force is required to make an object speed change. Therefore, the unbalanced force, the speed will decrease, and the net horizontal force is opposite to the direction of the motion of the bird. Can you see that last part? Opposite to the direction of the motion of the bird. If you don't add that, you will not get excellence. Okay, now this is a really bad diagram because from this I cannot tell which way the bird is flying. Okay, so I probably needed to use a simpler picture over here. But anyways, now referring to the force diagrams, explain the link between the horizontal net force acting on the bird and the type of motion. Describe what is meant by net force. So again, it's this definition that you need to know. and net force is the resultant overall total sum of the forces of an object. When multiple forces interact, if the forces are pointing in the same direction, the forces are added, giving a larger net force. If the forces are pointing in opposite direction, the forces subtract, giving a smaller net force. Net forces determine whether the bird is accelerating, decelerating, or maintaining constant speed. If the net force is pointing in the same direction as the direction of the motion, then the object accelerates. We've said this before. Same direction as the direction of motion, then it accelerates. If the net force is pointing in the opposite direction to the direction of motion, the bird decelerates. And if there's no net force, the bird maintains constant speed. Okay, is that clear? Those are the words we need to unpack. Use these words with the direction of motion, or opposite the direction of motion is deceleration. Okay. Alright, so firstly, let's have a look at this. Explain how the forces acting on the harvester result in the motion shown in the graph. No calculations are required. Include reference to the net force. So why don't you, let's just quickly unpack this. So number one, there's no calculations needed. Okay, now the forces acting on the harvester results in the motion shown in the graph. Include reference to the net force. Now let's just see. Okay, so this is a speed time graph, and we have two sections, section A and section B. So quickly pause and figure out in your head how you can answer this, please. Alright, welcome back. So in section A, this one over here, we start at 7 meters every second. When we end at 200 seconds, what's our speed then? It is still at 7. What do we call that? We call that constant speed because it's a flat line. Alrighty? It's a constant speed. So in a constant speed, what do we know about forces? All the forces acting on the tractor, the thrust, the friction, the gravity, and the what do you call it, the reaction force is equal. So thrust and friction is going to be the same size, as well as gravity and reaction force. Okay, and because of that there is no net force. And a net force, they said we have to give reference, so they want us to explain what a net force is the resultant force of all the multiple forces acting on an object. If they are in opposite directions, we have to subtract them from each other. If they are in the same direction, we have to add them together. Alright, so there you go. Let me just erase this quick. Excellent. Now section B. On section B we have our initial velocity is 7. Our final velocity is 5. So final velocity minus initial velocity gives us -2. So we are decelerating. Okay, we are decelerating, and that deceleration took us another 200 seconds. Now if you are decelerating, is your thrust force bigger or is your friction force bigger? Your friction is bigger than your thrust. Okay, and is that net force with the motion or against the motion? It's going to be against the motion, because if it was with the motion, the tractor would have gone faster. Okay, so it's not a tractor, I know it's a combine harvester, but yeah, you know what I'm trying to say. Okay, so section A, constant speed, the thrust force equal to the friction force, the net force is 0 Newton. Ooh, that's a good idea. We should, if we know that the net force is 0, and remember, force is always in Newton. Section B, decelerating, the friction force is greater than the thrust force, the net force is not 0, and the forces are unbalanced. Nah, that's not a good answer. The friction force is greater than the thrust force. The net force, the resultant force, is against direction of motion, therefore slowing down or decelerating the tractor. That would have been a better answer. Okay, in 2017 they talked about the crane. So question 3C, referring to the force diagram below, this one over here. Explain the link between the vertical net force acting on the container and the type of motion produced while the container is being lowered. In your answer, you should describe what is meant by net force and explain the link between the direction of the vertical net force and motion. So, you see my gravity is a big arrow and my lift is a small arrow. So which way is this thing going? Which way is it being accelerated? Okay, now they tell us it is being lowered. So from that we know that our direction is downwards. This is not a force, this is simply our direction. But is it accelerating downwards or is it going downwards at a constant speed? So then you can just say that your downwards force is bigger than your resultant force or your lift, which means that in this case it is accelerating downwards. It means that our net force is greater with the direction of motion, or in other words, downwards. Also, describe what is meant by net force. We've talked about that definition a lot now. So net force is the resultant force when they are opposite to each other. You subtract them when they are in the same direction. You add them. So net force determines whether the container is accelerating, decelerating, or maintaining. If the net force is pointing in the same direction as the direction of motion, the object accelerates. If the net force is pointing in the opposite direction, the object decelerates. If there is no net force, the object maintains at a constant speed or is stationary. The container is accelerating towards the ground with the direction of motion. It should have been in there. This is because the net force is pointing downwards with the direction of motion, and this occurs when, in this case, gravity is greater than friction. Okay. And yeah, so guys, can you please have a look at your side pads, pages 30 to 38. I hope you have a great day. I hope you understood this. There's no calculations. It's just an understanding of the forces. Alright. May the force be with you. Haha. Have a great day. Bye.